So now we're going to take a look at time payments, which usually involve long-term loans such as housing loans or mortgages. Okay, and we know that usually paid off through regular installments with compound interest charged on the balance owing at any point in time. So the calculation is actually similar to annuities, but it's actually a little bit more complex, right? It's more algebraic in nature because we try to establish things through a recursive formula. Okay, and the reason why it's actually going to be more complex is because we don't actually know the balance owing at any specific point in time. So we need to generalize a pattern, right? To demonstrate this idea, let's check out example 1, in which we've got Jennifer, who secured a $10,000 bank loan to be repaid in 2 years by equal monthly installments, right? So I'm going to draw a timeline and I'm just going to put all the information on it. So right now, what I know, right, at t is equals to 0, which is now, let's say that Jennifer takes out $10,000 from the bank. And then we know that interest is calculated monthly, 12% per annum on the remaining debt. So if the interest rate is 12% per annum, and we know that interest is calculated monthly, then the interest rate that we're concerned with is actually 1% per month, right? So that's what we're going to be dealing with. So interest calculated monthly is charged at 12% per annum on the remaining debt. We want to calculate the monthly repayment if the first repayment is 1 month after the loan is made. So usually when we're talking about repayments, okay, we usually start the repayments 1 period after the loan is made. There's no point making a repayment the day you make the loan, because why not just borrow less money, right? So now we don't know how much we're repaying, right? So let's let the size of my monthly repayments be equals to M, okay? So at t is equals to 1, I'm going to pay back M dollars. And then at t equals to 2, I'm going to pay back M dollars. At t is equals to 3, I'm going to pay back M dollars. And obviously the size of my monthly repayment is kept constant, right? And we're going to make these repayments all the way up until t is equals to 24, which is at the end of the second year, right? And then once again, you make a repayment of M dollars, right? And with this repayment of M dollars, you're assuming that you have cleared the $10,000 loan, okay? And you owe the bank nothing. So the way in which we're going to do this, right, we know that we're owing $10,000 at the very beginning. So how much money do we owe at the end of the first month after the repayment is just made? So let's let AM be the balance owing. Okay, so M in this particular case is equals to monthly repayment. And I'm going to let AN equals to balance at t is equals to n. If the question uses another letter to denote balance, sometimes they like to use bn as well, okay? Then obviously do what the question wants. But in this case, since the question doesn't specify, my standard notation is an. So if I check this out, right, then the balance owing at the end of the first month, right, A1, is going to be equals to, well, Jennifer borrowed $10,000, right? That $10,000 through the period of the first month gains interest. So it's going to be 10,000 times 1.01. After the interest is accrued, then you make your repayment of M dollars. Okay, so I'm just going to leave like this. Don't worry about finding 10,000 times 1.01. I'm not interested in the numerical value right now. I'm going to generalize a pattern through a recursive formula, so I need this in this form. So if I check out how much money Jennifer is owing at the end of the second month, then A2 is equals to the amount of money that you owe at the end of the first month, which is A1. That balance gains interest from t is equals to 1 to t is equals to 2. So it's going to be A1 times 1.01. After it accrues interest, then you make your M dollars of payment, right? So take note that A1 right now is equals to 10,000 times 1.01 minus M. That's from the previous part. And I'm going to take A1 and I'm going to multiply that with 1.01 minus M. And if I expand the whole thing, that's going to give us 10,000 times 1.01 squared minus M times 1.01 minus M. And here I'm just going to factorize the M times 1.01, right? The M out of the two terms at the back. So what we get here is 10,000 times 1.01 squared minus M times 1 plus 1.01, right? So now that we have A2, I'm going to go one more step further. I'm going to go from t is equals to 2 to t is equals to 3. So what is the balance at the end of the third month? Well, A3 is equals to whatever the balance is at the end of the second month. It accrues interest, and then we make the repayment of M dollars. So that relationship there is actually going to be quite obvious, right? Because we've been doing this over and over again. So A3 is actually going to be A2, which is the balance owing at the end of the second month. It accrues interest, and then we make a repayment of M dollars. From this, we can see that A2 is given by 10,000 times 1.01 squared minus M times 1 plus 1.01. And then we're going to multiply with 1.01 on the outside minus M. So if I take this expression and I expand the whole thing, right, so I need a new slide. So A3 is going to turn out to be equal to 10,000 times 1.01 cubed minus M bracket 1 plus 1.01 times 1.01 minus M. So if I take the 1.01 here and multiply into the bracket, then what that gives me, right, so I've still got the 10,000 times 1.01 cubed minus M times 1.01 plus 1.01 squared minus M. And now I'm going to factorize the M out from the last two terms, and that's going to bring us to the expression 10,000 times 1.01 cubed minus M times 1 plus 1.01 plus 1.01 squared. And by now, this is the reason why I do it up to A3 and why I didn't actually, for example, in the previous part with A2, the 1 plus 1.01, right? This is the reason why I didn't write this as 2.01, because what I'm looking for is a pattern. And what I should be able to recognize here, right? If I check this out with A3, A3 corresponds to 10,000 times 1.01 to the power of 3. So the 3 in the subscript corresponds with the 3 in the power over here. Inside the bracket next to M, I should be able to see that we have a geometric series forming where the highest power of 1.01, in this case is 2. 2 is 1 less than 3. Okay, so put that at the back of our mind. If I come back to verify this relationship with A2, right, where the subscript is 2, my highest power here, 10,000 times 1.01, right, that's raised to the power of 2. And then inside the bracket here, I've got 1 plus 1.01 to the power of 1. And this power here is 1 less than the subscript. Okay, so take note of this because it's important. That's why I need to do the relationship all the way up to A3 to formulate the pattern. Simply doing it up to A2 isn't conclusive enough. Okay, so now if I come back to A3, what this pattern essentially is telling me is I can take this and I can generalize it further. And what I'm going to generalize this to is A24, right? Because T is equal to 24, I want the loan to be paid off. So I want to know what A24 is as an expression because I want A24 to turn out to be equal to 0, right? I want A24 to be 0 because I want nothing left on the loan. I want the loan to be repaid completely. So if I check this out, okay, so generalizing this relationship, we should be able to see that A24 is equals to 10,000 times 1.01 to the power of 24 minus M, and then I've got a geometric series happening. So it's going to be 1 plus 1.01 plus 1.01 squared, and I'm going to continue adding powers of 1.01 until 1.01 to the power of 23, right? And I stop at 23 because this is 1 less than the subscript, which is dictated by the previous patterns that we saw. So what we're supposed to recognize now is that the 1 plus 1.01 plus 1.01 squared, right, all the way to 1.01 to the power of 23, we should be able to see that this is a geometric series. So we've got a GP where the first term is equal to 1, your common ratio is 1.01, and N is equal to 24, right? There are 24 terms because starting from 1.01 to the power of 1 all the way to 1.01 to the power of 23, that's 23 terms. And if I include the 1 at the beginning, that makes it 24 terms. And if we are adding a GP, we know that Sn is given by A brackets r to the power of n minus 1 over r minus 1, which means that A24 in this particular case is equals to 10,000 times 1.01 to the power of 24 minus m times A, which is 1, r to the power of n minus 1 over r minus 1. And what I need this to become is I need this to become 0. Okay, so but A24 is equals to 0 for the loan to be repaid within 2 years. So what that means is that 10,000 times 1.01 to the power 24 minus m times 1.01 to the power 24 minus 1 over 1.01 minus 1, which is 0.01, has to be equal to 0. And this allows us to solve for m, which is how much Jennifer needs to repay at the end of every month. Okay, so rearranging this, we get m times 1.01 to the power 24 minus 1 over 0.01 is equals to 10,000 times 1.01 to the power 24. Therefore, m is equals to 10,000 times 1.01 to the power 24 times 0.01 over 1.01 to the power 24 minus 1. So that's essentially what we have for Jennifer's monthly repayment. And if we plug all of this into the calculator, we're going to end up with a value of $470.73, right? So that's how we calculate reducible interest type problems. And we can see that in terms of the idea behind the question, it's actually not too bad. But what is actually pretty bad is just the tedious algebra. Okay, obviously over time, as we get more and more familiar with this, we can essentially start skipping lines. But for now, it seems extra tedious because I'm writing out every single line, right? And remember when we're setting up the recursive formula, I definitely recommend us to do it all the way up to A3, because if you do it up to A2, the relationship that we see isn't conclusive, right? So if we want to generalize, show up to A3 and then generalize, okay? And the second piece of advice is after a while of doing this, a lot of us start seeing a pattern. Please don't memorize any patterns that come out of this. What we're supposed to be able to do is set this up from scratch and use series and sequences to deduce anything that we want to come out of this, right? Or in other words, using a GP sum. If you guys were doing financial mathematics in uni, yeah, there is a formula for dealing with these type of problems that calculate the size of monthly installments straight away, but please don't use such formulas, right? What we're looking for in this particular case is developing the formulas ourselves through use of series and sequences, right? And that's very important. This concludes our first look at time payments.